In this video, we'll set the stage for what's to come with regular sets in terms of both definitions we've introduced, and set a to-do list on the topic. Let sigma be some finite alphabet. We now have two definitions of what it means for a set W in sigma star to be a regular set over sigma. W is the language accepted by some DFA over sigma, or W can be constructed from finite subsets of sigma star via sums, products, and asterisks. Or equivalently, W is given by some regular expression over sigma. Note that in both cases we're defining what it means for a set of strings to be regular, but we've given two disparate formulations of the concept. Note well that when we just say regular sets with no qualifier, we mean DFA regular. We're using these qualifiers just to keep things clear until we show they're logically equivalent. Here's what we've already deduced about regular sets from each of these viewpoints, which we'll label DFA regularity and set regularity. We found DFA as accepting the empty set and the set sigma star of all strings, and we've seen that we can find a DFA accepting the complement of any DFA regular set. On the other side, the definition of set regularity immediately shows that finite sets are set regular, as well as the sum, product, or asterisk of set regular sets. Thus the empty set, which is finite, is set regular. And asterisking the finite set sigma shows that the set sigma star of all strings over sigma is also set regular. An important note should be made at this point. When we say unions, intersections, and products, we mean the union of two regular sets, the intersection of two regular sets, and the product of two regular sets. This means that the intersection, union, or product of any finite number of regular sets is regular. For example, if U, V, and W are regular sets, then so is U union V, and thus so is U union V union W. This does not say anything about the union, intersection, or product of an infinite collection of regular sets, because there is no conclusion possible for these. We'll see later that the set a to the n b to the n, where n is greater than or equal to 0, is not regular, but it is the union of an infinite collection of singletons, each of which is regular as a finite set. Thus we cannot hope for infinite unions or intersections of regular sets to be regular. Indeed, if they were, every subset of sigma star would be regular, and there would be nothing to discuss. At any rate, this chart helps us to build our to-do list. On the DFA side, first we'll talk briefly about what we'll call Strees as a tool to visualize sets of strings, via which we'll be able to quickly show that any finite set is DFA regular. Next, we'll talk about the product construction for DFAs, which will make short work of the fact that the intersection or union of two DFA regular sets is regular. Non-deterministic finite automata and the subset construction will help us to show that the product of two DFA regular sets is regular, as well as the asterisk of a DFA regular set. Finally, we'll make this connection complete by showing that DFA regularity and set regularity mean the same thing. Given any regular expression, we'll show how to construct a DFA accepting the set defined by that regular expression. And given any DFA, we'll show how to construct a regular expression for the language it accepts. Via these two results, we'll complete the chart, because the left and right columns are logically equivalent. We won't show directly that set regularity is preserved under complements and finite intersections. If you're following along closely, you realize that we could almost justify all this immediately if we simply prove the equivalence of DFA regularity and set regularity first. But non-deterministic finite automata and the product construction are important concepts in their own right, and we'll see that NFAs play an integral role in proving that equivalence in the first place, so we're not just wasting time with them. Let's fix our alphabet sigma as the set 0, 1 for the time being. Everything we say can be applied to any alphabet we like. We can use what is essentially an infinite-rooted tree to organize our view of the set sigma star of all strings over sigma. We'll call this infinite tree of strings a string tree, or Stree for short. This is a made-up word which has two advantages. First, it carries no linguistic baggage, and second, it plays hell with autocomplete and autocorrect, which is fun. We construct a tree for our alphabet sigma as follows. We put a vertex at the top of this tree as its root, corresponding to the empty string. Each vertex in our tree will have a child vertex for each letter of the alphabet. Perhaps this looks familiar. For our alphabet, we'll make a left child for 0 and a right child for 1. We append that symbol to the parent string to obtain the string for each child vertex. So these first two children will correspond to the strings 0 and 1. We'll remind ourselves of that via the key at the top, and just remember that left is 0 and right is 1, to avoid cluttering our tree up too much by labeling all the edges. Continuing to these two new vertices, our string 0 has two children, 0, 0 and 0, 1. and our string 1 has 2 children, 1, 0, and 1, 1. We can continue building this tree one row at a time forever, obtaining a landing spot for every string in sigma star, though of course we can't draw the entire thing on the screen. In the case of our alphabet sigma, this gives us an infinite binary tree, in which every vertex has 2 children. The only difference for any other finite alphabet is the number of children at each stage, but the construction is the same. Also, technically the labels on each vertex are redundant. We can find the string for any vertex by reading the labels from the edges along the unique path from the empty string at the top to our chosen vertex. There we have the top of the tree for sigma star. A few observations. First, as we've constructed this tree, each row gives the strings of a given length. The empty string, then the strings of length 1, then those of length 2, etc. Second, within each row, the strings have been sorted lexicographically. Finally, this tree demonstrates the canonical ordering of the strings over 0, 1 if we read the strings top to bottom and left to right, in order by length, then lexicographically. Sigma star consists of the empty string, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, etc. This also shows us that the set sigma star is countably infinite if you know what that means. How is this tree useful? Well, every subset of sigma star can now be visualized by coloring the appropriate vertices of this tree, green for strings that are in the subset and red for those that are not. And the regular sets consist of certain subsets of sigma star. For the empty set, we color all vertices red. For the whole set sigma star, we color all vertices green. Our regular set 0 to the m, 1 to the n, where m and n are greater than or equal to 0, has a nice picture as well. These are the vertices we can get to by moving down and left for some number of steps, then down and right for some number of steps, but not changing directions again. Some sets, on the other hand, are not regular, such as 0 to the n, 1 to the n, where n is greater than or equal to 0. Note that the powers of 0 and 1 are restricted to be equal in this set. We'll prove that this is non-regular before we leave the topic of DFAs and regular sets. To be clear, the fact that our earlier set is regular and this one is not regular isn't something that you can necessarily see in this tree, but this tree at least lets us visualize the sets we're talking about. As an exercise, visualize in this tree what a complement, union, or intersection would look like to help give a concrete picture of these operations. With a bit more difficulty, you can visualize products and asterisks via a tree as well. We'll see Strees occasionally in the future, but for now, how can such a tree be used to help us construct a DFA that accepts a given finite subset of sigma? The process is wonderfully simple. Let a finite subset W of sigma star be given, and represent it by coloring an infinite tree green and red. To turn this tree into a DFA, make the top vertex the start state, and make each element of W into an accept state. This isn't quite a DFA yet for a critical reason. A DFA can only have a finite number of states. If we lifted that restriction, what we've just done would show that every set is regular, which again we know is not the case. But with only a finite number of strings in our set W, there must be a longest string in the set. We'll keep one row below this longest length and chop off the rest of the tree. Then make all of the loose ends into reject sinks. It is easy to see this DFA accepts exactly the strings in W. A short string in W will land us on an accept state. A short string not in W will land us on a reject state, and any string longer than the longest string in W will get us to the bottom row of reject sinks and thus will also be rejected. That's it. How to construct a DFA accepting any given finite set of strings. Do note that this is indeed a DFA. It has a finite number of states, including one start state, a transition from every state for each symbol of sigma, and some subset of the states marked as accept states. So we can add one more checkmark to our table. We've just compared and contrasted our two notions of regularity, one via DFAs and one via constructions of sets. And we set out a plan for the near future. To use the product construction to show that the intersection or union of two regular sets is regular, then to use non-deterministic finite automata to show that the product of two regular sets is regular, as is the asterisk of a regular set. Finally, we'll show that these two notions of regularity are logically equivalent, after which we'll prove the pumping lemma, and use it to show that some sets, including our set A to the m, B to the n, are not regular.